Okay, let's get started. Sorry for the delay. I'll try to be a little bit faster. I'll go very fast, I suppose. The faster the better, right? Anyway, okay. I'm going to give a little overview of conventions as emergent and persistent Nash equilibria. If you'd arrived in Japan when our borders reopened in late 2022, around November, and you'd taken the train up from Haneda Airport to Shinagawa Station, you'd have been greeted with a view something like this you see here. And you might have been a little surprised, right? You might have said, well, there must be some kind of stricture in place. There must be some kind of orders that people are following. But no, not at all. There were no rules per se, no legal or formal requirements to wear face masks at all, then, or in fact at any time from the start of the pandemic until then. But somehow we got from effectively almost no mask wearing, except in special cases for pollen and such, to this. And we were there, and this was what was happening this was Japan, November 2022. And if you went to, say, Paris at that time, it's very, very different. So you wonder why, and you think about how you can model these things. Now, there was this great book by this chap, David Lewis, a philosophy book, but also a game theory book. And it's called Convention of Philosophical Study. And he wanted to study conventional behavior and to model conventional behavior. And he defined it as conventional behavior amongst members of a population in a given situation is a regularity, such that everyone conforms to the regularity, everyone expects everyone to conform, and given that everybody else is conforming, you would wish to conform yourself for whatever reason. It could be manners, for example. It could be holding doors open for other people. You don't want to be the rude person. You don't want to hold a door when you're not supposed to hold a door, if that's what the society you're in does. And mask wearing. If you're the only person amongst a few hundred who's not wearing a face mask, you feel seen. And generally, we don't want to feel seen. There are other things like, veiling, other modesty clothing rules, road rules, handshaking versus bowing. It's awkward if you get it wrong. If you bow and they're sticking their hand in your stomach as you bow, it's awkward to miscoordinate. And circumcision as well is one of these things. And he was very impressed with Nash equilibrium. This book's, I think, 1969, so it's not too long after the Nash equilibrium concept had been developed and was spreading. And he used it to analyze these things. And you can see that 1 and 3, everybody conforms, and given that everybody else is conforming, you wish to conform, make this a Nash equilibrium. Now, of course, he was aware that in the real world, you will get someone who says, well, even though everybody else is wearing a mask, I'm going to walk around without a mask and I don't care, right? You will get outliers. So in the chapter Convention and Refined of his book, he refines it, and refining really basically here means weakening the conditions in places by adding most. So you weaken the definition so that you can reconcile theory with observation, so that most people conform most of the time, and most people mostly expect most people to conform most of the time, and given 1, most people wish to conform most of the time. And if we're thinking, you can understand this as perturbations. If you've got some kind of behavior that sustains a convention, you can understand this as perturbations of that behavior that would sustain an ideal convention. The ideal convention being the definition we saw on the previous page. And so you may have one or more of actions, expectations, or preferences being noisy. So perhaps your preferences are a little bit unstable over time. Sometimes you wake up in the morning and you just want to eat something unusual for a change. You're in a bad mood, you don't care. You don't care about what other people are doing, for example. So Can you formalize this? Yes, you can formalize it. You can, so very attractive gentleman. So you can apply it to a non-cooperative game as typical set of players, set of strategies, set of payoffs, and you can define something very important. You can define a behavioral rule for a player I. And the behavioral rule is going to say, given where we are, what should I do right now? You can make it more sophisticated, but for the purposes of this talk, let's assume, given a current strategy profile, what should I do? That's the behavioral rule. And you see there's a little epsilon there. That's usually measuring how big your perturbations are from some ideal. And your ideal might be best response, the kind of behavior that would sustain a Nash equilibrium. And, well, a little more formally, it's, you can think of it as a Markov process. So this is just a one person's behavioral rule. And if I'm following a behavioral rule, I can change my own behavior. So it says from a given strategy profile, what's the probability that we go to another strategy profile? Well, what's the probability that I change so that the overall profile changes to another strategy profile? And you can write that like this. And what restrictions you want to put on it? You see here we have the probability of moving from S to S dash under that Markov kernel. What restrictions do you want? Well, you don't want to be able to change other people's actions. At least for now we don't. We can just restrict that I can only change my own strategy, Bary can only change Bary's strategy, Eric can only change Eric's strategy. So that's a restriction on the behavioral rule. It's typical to assume that if we let perturbations go to zero, we converge to something, some ideal, the ideal behavior, the best response, or some best response. Also, regularity assumptions that I am not about to tell you. So, not hugely controversial, but anyway, we see. So we let an overall process be constructed in the following way. So each period, we'll take some discrete time, go t equals 1, 2, 3, 4, and we'll select an updating player according to a probability measure with full support on the set of players. So we randomly select some player, and then that player will update their strategy according to a behavioral rule. And so you can define an overall process according to that. You choose one player to update, and then you update the strategy profile according to player I's behavioral rule. And that gives you an overall process. You'll see we have an aside. In general, you can define behavioral rules for subsets of players as well. I could define a behavioral rule for whenever Tom and I are acting as a coalition, for example. Even if we weren't acting as a coalition, you could define a behavioral rule to account for some kind of correlation in what we do, right? Perhaps we're just mystically connected across time and space. And through these mystical signals, there's some degree of correlation involved in the changes in our behavior. But for that, we'd want to define a rule for M, where M would be both of us. Anyway, we have an overall process, and you can ask questions about what happens. So you define a process, you take the lever of the process and you pull it, and then it plays. Right? You press the play button, things happen, and you want to know what happens under this process. And so you can ask questions about predictions over different timescales. If we start the process here, where are we likely to be tomorrow? If everyone's wearing masks now, where are we likely to be tomorrow? Probably everyone will also be wearing masks tomorrow. Your prediction for some time from now may well be different. And you can also consider time averages over long horizons. So if you take a long horizon, and let's say you take the invariant measure, let's assume a unique invariant measure of the Markov process, and then you can also, if you want to consider a small perturbation limit, you can do that. You can take the limit as epsilon goes to 0, and another innovation of Peyton's. And if you're limiting measure is more than 0, we say that S is stochastically stable. It's the kind of meaning that the amount of time the process spends at that strategy profile doesn't go to 0 as your chance of perturbations, as your perturbation probability goes to 0. Other than this, you could also, because of assumptions on the probabilities, effectively probabilities of changes under these behavioral rules can be ranked in these models by order of magnitude, and you can use those to build a ranking of all of the strategy profiles according to something known as stochastic potential, which can rank all the strategy profiles in terms of how likely they are in the long run in a small perturbation world, and then the winner under that stochastic potential function is the stochastically stable outcomes. So I shall, in the time we have, rush through a few of the lessons that we have learned from this literature, and it's not going to be in chronological order, right? So I'm not going to start from the very beginning as Julie Andrews or whoever would. So you should start a little bit later on and then see how it relates to the beginning. So I'll start on something I worked on myself, which is asymmetry and stability. The idea that you can have a behavioral rule that's asymmetric towards a given strategy, and then this asymmetry of one person's behavioral rule, if everyone has rules that are asymmetric in the same direction, this leads to societal forces that push you towards everybody playing the strategy towards which our rules are asymmetric as a stochastically stable outcome. Well, this is what I just said. What do I mean by asymmetry? What does it mean for my behavioral rule to be asymmetric towards a given strategy? Let's say asymmetric towards red. So first, we'll define an idea of red association. So here there's two strategies, red and transparent. You can think of transparent as being anything other than red. And we have two strategy profiles. We have the one on the left and the one on the right. So you see, and I've marked Alice as a single player. So we have S dash and S dash dash dash. And if you take those strategy profiles and you overlay them, you put one on top of the other. Remember, we have red and transparent, so you can see the red shining through from the bottom. You'll notice that when you overlay them, you end up with all red. So any pair of strategy profiles such that after you overlay them, it's all red, are said to be red associated. And then we'll define asymmetry. We'll say what asymmetry means. Asymmetry towards red means that you'll notice Alice up here. At one of these, she's playing white, and so might be thinking about switching to red. And at the other, she's playing red, and so might be thinking about switching to white or transparent. Yeah, one switching to, one switching away. And asymmetry means that the probability that she switches to red at this one is at least as big as the probability that she switches away from red on this one over here. And it's measured in orders of magnitude, but we can hand wave that away given the time constraints we have today. This is, you'll notice that if we switch that top right-hand red one to a white, we would have changed everyone's strategy across from S dash to S double dash. So you would be looking at a kind of the opposite of ceteris paribus, right? Be like all else being different, Alice should be more likely to switch to red here than away from red in a different world. And then if we add extra reds, that doesn't break that. You still maintain a coordination motive. So this is what it means to have an asymmetry, right? There's a small or large, bias towards red in the behavioral rule of Alice. If everybody has such a bias, it aggregates to the process as a whole. So an asymmetry for a process as a whole was something that Pesky discussed in a paper of his. And this turns out to imply stochastic stability. So if every player has a behavioral rule that's asymmetric towards red, then everybody playing red is stochastically stable. It's something that happens with positive probability even when error rates go to 0, even when perturbations go to 0. Can you get a strict version of this? Yes, you can. Make something strict, you define a strict asymmetry, and you get there. Why is this interesting? Well, it's moving up from the individual, and it's aggregating. And I've only said that individual rules are asymmetric towards red. I haven't said they play the same rule, right? So we could all be playing very different behavioral rules, but as long as they all have a bias towards the same target strategy, we can aggregate and end up having that as a, I don't know if I want to say prediction. No, let's say prediction. A plausible outcome.
Excuse me?
Yes?
This condition holds for any S prime and S double prime whose overlay is everything red?
Yes.
For example, like, where does this come from? For example, like, like if everything is white except one node in S prime, and like almost everybody is red in S double prime, is that like, like, what type of behavior would, like satisfy this with like, like S prime and S double prime is like very loud?
Okay, what type of behavior? Let's,
just an example, just a picture.
Okay, so I'm thinking of, I'm just
asking it for all possible S prime and S double prime.
Yeah.
Like S prime being almost all white and S double prime being almost all red, and vice versa.
Yeah.
You want still Alice to, this inequality will hold.
Yeah, because you're talking about, say, all white and one red versus, say, all red and one white.
Yes.
And where might asymmetry come from? It might come from a cost inherent in it. Let's say you're looking at an intergenerational model and you are thinking of whether to bind the feet of your daughter, something along these lines, right? And you have some coordination incentive. You want to do what society's doing. On the other hand, it could be the case that if you yourself have complied with this, if you yourself have had your foot bound, it could create a stronger belief in the goodness of the custom than the level of disbelief you might have if you haven't had your feet bound. And so that might make you less likely, or also more likely, to do the same as you've done for your own children in the case of foot binding. So you can think of it, well, we'll see one very famous example in a second of where these biases arise from. But essentially, there's some reason that you might not want to switch away from red in exactly the same situation, but reversed, compared to white, compared to transparent. But bear with me, we'll see the most famous example in a second. It's behavior based on payoff differences. So I like this parameterization of coordination games. We have two parameters. We have alpha, so this is a symmetric coordination game. Equilibria AA and BB. And two-player game. I like this parameterization. Alpha gives the potential advantage in terms of potential function of A. So AA is a risk-dominant equilibrium. Beta is the payoff difference between AA and BB. Could be positive or negative. Let's look at a game where the payoff of player I is a weighted average of playing this game against, well, some subset of the other players. So he's playing on a network, effectively. The influence of player J on player I is given by this W here. And so this share of player I's payoffs comes from playing this game against player J. And they play the same strategy against all players. You're playing A or B. It's a coordination game played on a network. Now let's have a behavioral rule. And there's a class of behavioral rules based on payoff differences. So the payoff loss for player I when changing strategy from S is this. This is the loss, or if it's negative, the payoff gain that player I would get from changing his strategy from SI to SI dash. Now, if the probability of player I changing strategy has an order of magnitude epsilon to the Fi of this difference, where this Fi is non-decreasing, this means the probability of changing your strategy increases weakly in the payoff gain from doing so, or decreases in the payoff loss from doing so. It's that class of rules, like higher payoffs are good, lower, so we're more likely to change to get higher payoffs, lower payoffs are bad, so you do the opposite. And it includes rules such as best response with uniform mistakes, which just says play a best response. And if you make a mistake, all mistakes are made uniformly. So there's this thing says if you're losing, if you have a positive loss, the order of magnitude of that loss is epsilon to the order of magnitude of probability of that loss is epsilon to the 1. So all mistakes are equally likely in some sense. All best responses are equally likely. This contrasts with logic choice, which is also in this class, which says if the loss from from a perturbation, from a non-best response, goes up, then your probability of making it, order of epsilon to the x, goes down. As the loss goes up, you're less likely to make it. You're less likely to make big mistakes. So it's a popular class of rules. And it turns out that if a player follows a rule in that class, then that behavioral rule is asymmetric towards the risk-dominant action. You can see that's kind of natural in some sense. Your behavioral rule is defined according to payoff differences, the differences between the payoffs from two strategies, and risk dominance is as well. Right? It depends on the difference between that and that, so 1 plus alpha, the difference between that and that, which is 1. And so that gives you asymmetry towards A. And if each player follows such a rule, then it's stochastically stable for everybody to play A. That follows from the earlier theorem. And it applies even if players have different payoff difference-based rules. Now, that basically summarized a lot of papers in the literature had, in a variety of special cases, dealt with risk dominance and stochastic stability. And you can go even further than that. You can actually, from a current strategy profile, you can allow a behavior to rather than say best respond plus perturbations to the current strategy profile, he can form a conjecture, right? Think, okay, other people are going to change their strategy. What can we do? He can form a conjecture and respond to that. For example, he could be a level K thinker. And it turns out that the key thing is that if we've got two possible strategy profiles that are A-associated, if the conjectures you form from those are also A-associated, then you are fine. Then the theory and the risk dominance's winningness continues. And that happens to be the case if you're using, say, K-level conjectures, K-level thinking, allowing you to best respond to other people's best responses, and so on and so forth. Okay, thank you. Perfect. Other things that have come from this literature, the importance of intermediate conventions. Intermediate conventions, so in this kind of coordination network setup, are conventions where not everyone plays the same thing. There's a few different ways you can get them, and they're important for a couple of reasons. So one way you can get them, so here's a network, is if you have this little cluster of people, so you have local interaction on this network, assume that, say, you have a weight of 1 for each of these, or then just no weight of people who have no connection. You can have local interaction, and in this case, you might get this little triangle of reds stuck playing red while everybody else continues to play white. And this could be a Nash equilibrium, and you're only going to leave that Nash equilibrium through some non-best response style behavior. So local interaction can give you that type of behavior. Of course, if there's a possibility of a coalition forming of those, if we allow non-individualistic rules, it's possible that they might seize the opportunity, because it's possible their payoffs could be higher, even though they're at a Nash equilibrium. It's possible that if they could simultaneously switch back to everybody playing transparent, they would have higher payoffs. So a coalition could actually move you away from that intermediate Nash equilibrium. And if really what you want, you have situations where what you want is for red to spread across the whole network. And sometimes the best way for red to spread across the whole network is for there to be an outbreak of reds who mutually reinforce one another's behavior, and from that little cluster, red spreads across the network, sometimes gradually. And so you see here how coalitional behavior can crush those incipient invasions of red in the population, and can sometimes work as a poverty trap where you have efficient local coordination working against efficient global coordination. Another way you can get intermediate conventions, even in global interaction, is if you, well, say this is global interaction. We take this model, and let's say you need 5 reds to get to the basin of attraction of red. So you'd need 5 people to somehow move to red with non-best responses for you to enter the basin of attraction of red and end up here. So in that basic model, there are no intermediate conventions, but if you add switching costs, you can get intermediate conventions, because at intermediate stakes, say for example, if 4 players play red, you could get a situation where the payoff from red and white is so similar that it's not worth your while changing your strategy. And so you end up getting stuck in the middle. But oddly, getting stuck in the middle can speed up the system's overall convergence to red, if that's where you're going. It can speed up the waiting time from going from an all-white profile to an all-red profile. And you can get a similar thing if you add a new strategy. Sometimes you might think, well, perhaps by adding a new strategy, you can create an intermediate convention. You can create a stepping stone. So in this case, you can add a green strategy such that it performs well when it miscoordinates with white, but badly when it miscoordinates with red. So it's easy for green to invade white, but then once green's invaded, it's easy for green to be invaded by red. This is a type of theory that's recently studied by Gillespie and al. When they're looking at female circumcision in Somalia, if I remember correctly, and asking if having an intermediate circumcision norm, not one that's introduced, but if the existence of that could speed up the system, or help the system, let's say, help the system move from a more severe circumcision norm to a non-circumcision norm. Their answer is negative. So the other, well, I do have time. 5 minutes is fine. The final point I'll make, though this literature has had an impact, is in surplus sharing and fairness, right? So in general, there's 2 things that can happen here when your behavioral rules interact with fairness norms and that determine which conventions are in some sense most stable. One is the effect of payoffs on your own behavior through, for example, logic choice, right? If a convention is offering you nothing, you have nothing to lose. And under some rules, such as logic, you'll be more likely to play non-best responses. And the other one is the effect of your behavior on other players. So if you combine these things and look at different behavioral rules playing on playing coordination games that represent, that map so you map the payoffs of a bargaining frontier to a coordination game, and then you allow populations under different behavioral rules to play this game, you can, according to the behavioral rule, have different conventions that arise. And somewhat sweetly, if you look at a class of rules that is uniform perturbations, logic perturbations, unintentional, so any perturbation has full support, perturbations have full support, versus intentional, which is where your errors are directional in the sense that if you play a non-best response, it always involves you asking for more. Right? So you always only play best responses that would be nice if they worked. If you pull a lever on those processes and see where you go, well, you go to Kallis-Borodinski bargaining solution under uniform intentional, the original Peyton dynamics. That's the result of Peyton's. You have this. If you make them intentional under uniform, Naidu, Huang, and Sam Bowles showed that you get the Nash bargaining solution. But if you do it for logits, you get something weird, or the logit effect nicely cancels out the effect of your actions on other people, and the egalitarian solution of, well, yours truly drops out. So that I find like a pretty result from this literature. So overall, I'd say those are some of the key things that have come from this literature over the years. Empirics, by the way, support payoff dependence and intentionality when we run these in the lab and measure what kind of non-best response behavior people were doing, and so that would support egalitarianism in this type of setup. Conclusion, I think there are kind of opportunities in evolutionary design, encouraging convergence to specific conventions. Bill Sandholm looked a bit at efficiency via Pigouvian pricing under logit. I've looked a bit at team sizing in organizations, and I have some current work on persuasion and conventions. And also, it's possible to just read positive results. You can flip them and say what they say as a design result as well. So if you look at recent work by Ariely and Arigapudi on, that's me, on fast convergence under signals, you can ask questions about what type of signals, what type of situations would you want to engineer to obtain fast convergence to a desired convention. And the same with the Gillespie paper I mentioned earlier. How could you change the situation in Somalia, right? What kind of policy changes could you make that would push you in the direction you wanted to go? If I'm allowed at least one, like, slightly snarky comment in this, just to end the talk, I'd say there are hundreds of papers on school choice. I read loads of these things every year, right? So I think there's space for a bit more on repeated situations in which, as Lewis said, members of the population may converge to a regularity. Thank you very much.
Okay, time for some questions. Johnny will choose.
Okay, I'll choose. Do we have any questions? I was probably too fast. Oh, you have no questions.
What does KIR stand for?
What? Oh, KIR, the Kyoto Institute of Economic Research.
Wow.
So, yes, it's not in honor of the Prime Minister. So that's not.
So on school choice, I mean, you would have to have a lot of children to really learn a lot about optimal strategy.
Yeah, I'm not saying it should be applied to school choice. I did write a couple of papers on matching and these dynamics, which is why I get asked to read so many papers on matching. You know, you pay for your sins.
Well, maybe dynamics on networks would be a good model.
Yes.
About school choice is, you know, I mean, the first, what you do, I mean, you ask somebody whose situation is like yours, what's the right way to do this? And it might be interesting to get data on how the populations change their behavior
for sure, in school, because in schools there are definitely certain behaviors you want to encourage, right? And I guess they're measurable as well. I mean, some of these, right? I mean, class disruption events. So that's something that could be, it could be modeled, but of course you could do experiments within schools on.
So I've seen data, I forget the references, but I've seen data on, the extent to which people figure out when the planners tell them it's optimal to report their true preferences and it's not true. There are data like that on how people respond over time.
Okay, yeah, that's almost a dynamic within a preference revelation mechanism. That's interesting in itself. Okay.
Any more questions?
I feel people want, oh, not quite, please.
I'm just wondering, there's a connection I see between your paper and Huguet's paper, which is like the idea is something like when you put that third, like, say you want to protect a convention and you put one in there which is kind of a fake one or something like that, just to make it so. I wonder if you can relate that to the robustness idea, right? Which is something like you put something in which, if they do deviate to this thing, they're not going to go any further at least. See what I'm saying? Like, I kind of see
yes.
that as
You could work in both ways.
Yeah.
You could put one in between that helps people to go helps people to go further, or you could do the opposite. You could create, aim to create a sink to prevent that from happening. You could, this was a finite population, but say if you deal with infinite populations, you could think of having a non-asymptotically stable equilibrium, and then you adjust something and it becomes asymptotically stable.
An example which occurs to me, in my college, we had this honor code so that we all took our exams separately. And so the idea was this discouraged cheating by just sort of, appealing to honor. But when I think about it, the key thing it did is it prevented cheating from spreading to other people. So it didn't prevent you from cheating, but it prevented you from talking about cheating with other people. So
yes,
because it was all separate. So I don't know. That seems.
No, absolutely. Prevented any kind of creeping or spreading normalization of that behavior through.
A related question to that, maybe a different way to look at it, is asking the question of what graphs are likely to arrive at a convention and stay there. Right. So you want to get there fast, maybe, but also like some interaction between the payoff matrix and the graph structure would dictate, I presume, how long it'll take you to form a convention, and how like the meta-stable state, which is the convention, how long you'll stay there.
So in general, if you've got very dense graphs, it can be very difficult to move from convention to convention. Less so in sparse graphs. But then again, it depends on the dynamic you're looking at. So I've looked at coalitional dynamics before, and in very sparse graphs, unless you can also lose, particularly if it's a random graph with relatively low clustering, you can miss the opportunity for coalitions to form to actually move in the direction you'd want them to move in some cases. But in general, denseness slows you down in the spread.
So in my book, The Individual Strategy and Social Structure, I talk about exactly this problem. And one idea is that if the graph has the property that locally people are tightly connected, I call this close-knit.
Yeah.
And if everybody is in a relatively small close-knit group, then you get quick convergence to the new norm in each of those groups separately, and then that can converge through a sort of contagion process to the whole network. So that's a kind of a localized way in which you can get fast convergence.
Yes, that's right. And actually, close-knittedness is really nice. It's like where you maximize potential by some group doing something no matter what other people outside the group do. And you can connect that. I mean, that's a graph property. And you take something like cohesion, like Morris's cohesion, which is also a graph property, and you can connect those through basically conditions on the alpha and beta in your coordination game. You can I'll mention it to you in a second. It's definitely lunch stuff. It's something I like, but is fairly abstruse. It's very nice. Thank you very much.
May I suggest we continue